Hi there, this is Estelle Trengove and this is part 2 of my video on Thevenin and Norton's theorems. In this video we'll look at source transformations, we'll look at Thevenin's theorem, Norton's theorem, and then we'll also look at a practical way of finding the Thevenin and Norton equivalent circuit by doing measurement on a real circuit. You'll remember that in the previous section we looked at real voltage sources and real current sources, and we saw that a real voltage source can be modeled as an ideal voltage source with voltage V open circuit in series with a resistor which we called RS, which is the source resistance of a real voltage source. We also saw that a real current source could be modeled as an ideal current source with current I short circuit in parallel with a source resistance RP. And we also saw that both the real voltage source and the real current source could be described by the equation V open circuit is equal to a source resistor times I short circuit. So you can see that if RS is equal to RP, we can either represent a source, so let's just call those all RS for as a source resistance. Then you can see that these two sources are interchangeable. So we can either we can transform a voltage source in series with this source resistance into a current source where we have the same resistance in parallel, and as long as the equation V open circuit is equal to the source resistance times R short circuit holds true. Thevenin's theorem and Norton's theorem both tell us that if we have a random linear circuit with two terminals that we can connect to, then these random linear two-port networks can be represented either by Thevenin's theorem or by Norton's theorem. And Thevenin's theorem tells us that a random complex linear circuit with two ports can be represented as a voltage source with voltage V Thevenin in series with a resistance of R Thevenin. And similarly, Norton's theorem tells us that a random complex linear two-port network can be represented as a current source with a current I Norton in parallel with a Norton's equivalent resistance R Norton So we're going to look at how to find the Thevenin equivalent circuit and the Norton equivalent circuit of a random complex linear circuit. So Thevenin's theorem says that if we have a random complex linear circuit, and that is connected via nodes A and B to a load, then we can find the Thevenin equivalent by removing the load. So now we've still got our random circuit as before. We've removed the load and we've got terminals A and B, and we're going to find the equivalent for the random circuit looking into nodes A and B. And it turns out that that random circuit can be represented by a voltage source, V Thevenin, and V Thevenin is equal to V open circuit, looking into A and B, and R Thevenin where R Thevenin can be found by turning off all the sources and finding the equivalent resistance. And that is Thevenin's theorem. So we'll look at using the Thevenin equivalent circuit and finding it by looking at an example. So say we have a circuit that has a 7.5 volt voltage source, and that's connected to a 5 kilo ohm resistor, and here we have a 10 kilo ohm resistor, a 15 kilo ohm resistor, we have a current source of 3 milliamps, and a 4 kilo ohm resistor, and we had a load resistor, but we've now removed that load resistor, and we're looking into terminals A and B. So the voltage here is VAB, and VAB, if you look in here, VAB is equal to V open circuit, and that is equal to V Thevenin. So if we can find the open circuit voltage here, then we will know what the Thevenin's equivalent voltage is. So let's use nodal analysis to find V open circuit. So to do nodal analysis, we've got to define a reference node. We're going to define it there. We've got to define some node voltages. So let's call this V1. We're going to call this V2. And we're going to call this V3. And let's call this current I1. We're going to call this current I2. Let's define this current I3 in that direction. And over here, we've got current I4. So if we look at the circuit, the first thing we notice is that V1 is equal to 7.5 volts, because you can see that this point V1, the only thing that's connected between V1 and our 0 volt reference voltage is the 7.5 volt voltage source. So V1 is equal to 7.5 volts. And then we can also see that because we've open circuited the circuit, there can be no current flowing here because there's nowhere for it to flow. There needs to be a connected path for a current to flow. So we observe that I4 is equal to 0 amps. There's no current flowing there. And because I4 is equal to 0 amps, at this point here, we've got 0 amps flowing out. And so all we've got flowing in here is the 3 milliamps from the 3 milliamp source. So we also know that I3 is equal to 3 milliamps. Now applying nodal analysis at node V2, we first find the Kirchhoff's current law equation, and we can see we've got flowing into V2, we've got I1 plus I3, and flowing out, we've got I2, so I1 plus I3 must be equal to I2. And then we write these currents in terms of the node voltages. So remember, V1 is 7.5 volts. So I1 is 7.5 minus V2 divided by 5 kilo ohms. I3 we saw was 3 milliamps, and that's equal to I2, which is V2 minus our 0 volt reference node divided by 10 kilo ohms. So if we multiply this out by 10,000 ohms, so this is just maths now, then we get 15 volts minus 2V2 plus 30 volts, and that is equal to V2. And if you do the maths, it turns out that V2 is equal to 15 volts. We can't really apply nodal analysis at node V3 because remember we've just got one current flowing in and one current flowing out. So we know that in a resistor the current flows from the higher voltage to the lower voltage. So let's call that Vx, and we know that Vx is equal to 3 milliamps times 15 kilo ohms. And so, because remember we said that I3 is equal to 3 milliamps, and so we know therefore that Vx is equal to 45 volts. And we also know that V3 minus V2 is equal to Vx, which is equal to 45 volts. And we've just calculated that V2 is 15 volts. So therefore V3 is equal to 45 volts plus 15 volts, and that's equal to 60 volts. And now if you look into terminals A and B, so if you're looking in this direction, then we can see there's no voltage drop across the 4 kilo ohm resistor. So in fact V3 is equal to V open circuit, and that is equal to V Thevenin. The other part of finding a Thevenin equivalent for a circuit is we have to find R Thevenin, and we do that by turning off all the sources. And remember we said in the superposition lecture that means that we turn the voltage sources to 0 volts. So voltage sources we replace by a short circuit, and current sources we turn the current to 0, so that is equivalent to replacing the current source with an open circuit. And we're going to do that in this circuit. So to find R Thevenin, you turn off all the sources, and then you use resistors in series and resistors in parallel to find the equivalent resistor. So if we replace all the voltage sources with short circuits, then we end up with the 5 kilo ohm resistor and the 10 kilo ohm resistor. This is the short circuit where we've removed the voltage source, and then we've got the 15 kilo ohm resistor, and that current source we replace by an open circuit. We still have the 4 kilo ohm resistor here, and here we've got nodes A and B, and the Thevenin equivalent resistance, R Thevenin, will be found by combining these resistors in series and in parallel. So you can see that the 10 kilo ohm and the 5 kilo ohm are connected by these two common nodes, so they are in parallel with each other, and 5 kilo ohm in parallel with 10 kilo ohm is equal to 3.33 kilo ohms. And obviously the 15 kilo ohm and the 4 kilo ohm are in series, so together they make 19 kilo ohms. And so we can reduce this circuit to a 19 kilo ohm resistor and a 3.33 kilo ohm resistor, and here we still have nodes A and B, and this is our Thevenin, and so we can see therefore that our Thevenin is equal to 19 kilo ohms plus 3.33 kilo ohms, so it's equal to 22.33 kilo ohms. And now remember that a Thevenin equivalent circuit isn't complete until we've actually drawn the Thevenin equivalent circuit, and so we found that the Thevenin equivalent voltage V Thevenin is equal to 60 volts, and that's in series with the Thevenin equivalent resistor R Thevenin, which is 22.33 kilo ohms. And Thevenin's theorem tells us that this circuit is equivalent to this circuit. But if you don't believe they're equivalent, then you can put a 10 kilo ohm load on both. So we connect our Thevenin equivalent circuit, which has a voltage source of 60 volts and a resistance of 22.33 kilo ohms, and this is node A, and we connect a 10 kilo ohm resistor, and this is node B, and that, if we work out VL, then by the voltage divider rule, we see that VL is equal to 60 volts times 10 kilo ohms divided by 10 kilo ohms plus 22.33 kilo ohms, and therefore VL is equal to 18.56 volts. I'm not going to do the calculation, but if you put the same 10 kilo ohm load on the original circuit with the 7.5 volt source, the 5 kilo ohms, the 10 kilo ohms, the 15 kilo ohms, milliamps, and 4 kilo ohms. And now we're going to connect that to the same load of 10 kilo ohms. Then you will see, if you use a technique like nodal analysis, you will see that VL1 is also equal to 18.56 volts. Norton's theorem says that you can replace a random linear circuit by a Norton equivalent current source with a current of I Norton, and a Norton resistance in parallel with it, and it turns out that I Norton is equal to the short circuit current if you put a short circuit across the terminals. So we've got our random circuit, our random linear circuit, and we short circuit those terminals. And that short circuit current, I short circuit, is equal to the Norton equivalent current source. And we find the Norton resistance equivalent in the same way as we found the Thevenin. So R Norton is equal to R Thevenin. And where we set all the sources to 0 and find the equivalent resistance. And so you can see, if you have calculated the Thevenin equivalent circuit, then we can also calculate the Norton equivalent current source, because I Norton is going to be equal to V Thevenin divided by R Thevenin. And finally, if you have a circuit in practical situations, it sometimes happens where you cannot measure a short circuit current or an open circuit voltage, then what you can do is you can find the Norton and Thevenin equivalent circuits using a variable resistor. So let's say we use resistors that we know the value of, and we're using resistors of 2 kilo ohms, 4 kilo ohms, 6 kilo ohms, 8 kilo ohms, and 10 kilo ohms, and we measure the voltage drop across that load resistor, and the voltage drop turns out to be 9.6 volts, 10.3 volts, 10.7 volts, 10.9 volts, and 11.1 volt. Then we can use Ohm's law to calculate the current, and the current is 4.8 milliamps, 2.6 milliamps, 1.8 milliamp, 1.4 milliamp, and 1.1 milliamp. Then we find the Thevenin and Norton equivalent by drawing a graph of those points. And we are going to plot the voltage against the current in milliamps, and the voltage in volts, obviously. And so we're going to plot those points, and we're going to do our best estimation of a straight line through all of those points. And now we know where that line, that curve that we fitted, that line where it intersects the y-axis, we know that when the current is 0, then this voltage must be V open circuit. And similarly, when the voltage is 0, then we know this current is I short circuit. And so by plotting these points, we are able to find the Thevenin equivalent voltage, because remember V open circuit is equal to V Thevenin, and we're able to find the Norton's equivalent circuit current, because I short circuit is equal to I Norton. And the slope of this graph gives us the Thevenin equivalent resistance. So R Thevenin is equal to V2 minus V1 for any point on that graph, divided by I2 minus I1. So the slope is negative, but obviously we just are going to use the modulus of that to find R Thevenin. And that is the end of this recording.